In 1935, Albert Einstein sat down with two younger physicists, Boris Podolsky and Nathan Rosen, and wrote a paper that he believed would end an argument. It didn't. It started one that's still going 90 years later, and along the way, it produced an experiment that did something almost no experiment in the history of science has done. It forced physicists to question whether reality, in the most basic sense of the word, actually exists the way we assume it does when nobody's looking at it. That's not a metaphor. That's not a philosopher being dramatic. That's the literal, technical conclusion of a body of experimental work that culminated in a Nobel Prize in 2022. And I want to walk you through exactly how we got there, because the path is one of the strangest and most satisfying stories in the history of physics. And I don't think you need a physics degree to follow every step of it. You just need some patience with a few genuinely strange ideas. And I promise by the end, they'll feel less strange and more like the most interesting thing you learned this year. Let's start with the discomfort. By the 1920s and 30s, quantum mechanics had already proven itself. It correctly predicted the behavior of atoms, the spectrum of light emitted by hydrogen, the stability of matter itself, things that classical physics simply could not explain. It worked in the sense that matters most to a physicist, meaning its predictions matched what experiments actually showed over and over to a precision that bordered on absurd. And yet Einstein, who had helped build the foundations of quantum theory in the first place, back in 1905, when he explained the photoelectric effect by proposing that light comes in discrete packets, hated what quantum mechanics seemed to be telling him about the nature of reality. Not because the math was wrong. The math was and is spectacularly accurate. He hated what the math seemed to imply about what's actually happening out there in the world, independent of us. Here's the implication that bothered him. In classical physics, the physics of Newton, of billiard balls and planets and falling apples, an object has definite properties whether or not you're looking at it. A ball has a position and a velocity right now, this instant, independent of whether any human being or measuring device happens to be checking. Quantum mechanics, as it was being interpreted by Niels Bohr and his colleagues in Copenhagen, seemed to say something different. It seemed to say that a particle doesn't have a definite position until you measure it. Before the measurement, it exists in something called a superposition, a mathematical description that assigns probabilities to many possible outcomes at once. And it's only the act of measurement that forces one of those outcomes to become real. You've probably encountered a simplified version of this idea before, the famous image of an electron passing through two slits at once and interfering with itself, producing a pattern on a screen that only makes sense if you accept that the particle, in some sense, explored both paths simultaneously, right up until the moment you try to catch it, doing so, at which point the interference pattern vanishes and the electron behaves like it went through one slit or the other after all. That experiment alone unsettled physicists for decades. What Einstein was reacting to went even further than that. Einstein found this deeply unsatisfying, not because he doubted the predictions. He trusted the predictions completely, but because he believed there had to be some deeper, hidden layer of reality, some set of properties the particle actually possessed all along, that the mathematics of quantum theory simply hadn't caught up to yet. He called this idea that objects have definite properties independent of observation, realism. And he believed, as most physicists before him had always believed without needing to state it explicitly, that realism was simply how the universe worked. Quantum mechanics, in the Copenhagen interpretation, seemed to be telling him he was wrong, and he wasn't ready to accept that, not without a fight. This wasn't a minor disagreement between colleagues. Einstein and Bohr argued about this in person at scientific conferences for years, most famously at a series of meetings called the Solvay conferences in Brussels, where the greatest physicists of the era gathered to debate the foundations of the new theory. Einstein would arrive with an ingenious thought experiment designed to expose a contradiction in quantum mechanics, some clever arrangement of clocks or boxes or particles that seemed to violate one of its core principles. And Bohr, often after a sleepless night working through the problem, would return the next morning with an answer that closed the gap usually by showing that Einstein's proposed measurement would itself disturb the system in exactly the way needed to preserve quantum uncertainty. Einstein lost these specific battles one after another, but he never accepted that he'd lost the war. He believed quantum mechanics was a successful but incomplete theory, the way, say, thermodynamics was a successful but incomplete description of gases, before physicists understood that heat was really just the statistical behavior of enormous numbers of individual molecules. He wanted the deeper underlying layer of quantum reality, and he set out with Podolsky and Rosen to prove that such a layer had to exist. So in that 1935 paper, Einstein, Podolsky, and Rosen tried a different strategy than the earlier thought experiments. Instead of hunting for a direct contradiction in quantum mechanics, they tried to show that the theory, if you took it fully seriously, forced you into a strange enough corner that it couldn't possibly be the last word on reality. And their argument hinged on a phenomenon that quantum mechanics predicted, but that on the surface seemed almost too strange to be physically real: entanglement. Let me build this up carefully, because entanglement is one of those ideas that gets thrown around casually in pop science, and it deserves better than that. Imagine you can create a pair of particles in a special way so that certain of their properties are linked. Not linked the way two socks from the same pair are linked, where each sock already has a definite color and you just don't know which one is in which box until you open it. Linked in a stranger way, a way where quantum mechanics says neither particle has a definite value for that property until one of them is measured. Before the measurement, both particles are described by a single shared mathematical description, a joint state that can't be broken down into this is particle 1's independent situation and this is particle 2's independent situation. They're not two separate things that happen to be correlated. In the mathematics, they're one combined system, even if you physically separate them and send them to opposite sides of a laboratory or opposite sides of a galaxy. And here's the part that made Einstein uncomfortable. The moment you measure one particle and force it into a definite state, the other particle, no matter how far away it is, instantly reflects the correlated outcome. Not reveals what it already secretly was, instantly reflects it, as if the measurement on one side reached across space and settled the matter on the other side faster than any signal could possibly travel between them. Einstein called this spooky action at a distance, and he meant it as an insult to the theory, not a description he was comfortable accepting at face value. His argument was essentially this: nothing can travel faster than light. That much we know from relativity, a theory he'd spent much of his career building. So if measuring one particle appears to instantaneously affect a description of the other, then quantum mechanics can't be telling the complete story. There must be some additional information, some hidden property carried by each particle from the moment they were created that determines the outcome of any future measurement in advance. Physicists later gave this hypothetical hidden information a name: hidden variables. Einstein wasn't saying quantum mechanics was wrong in its predictions. He was saying it was incomplete, that underneath the probabilities there had to be a deeper, more classical layer of reality that filled in the details, the way knowing the exact position and velocity of a billiard ball fills in details that a purely statistical description would leave out. For about 30 years, this stayed largely a philosophical dispute. Bohr responded to Einstein with his own paper defending the completeness of quantum mechanics, and the two of them went back and forth respectfully but firmly for the rest of their lives, never fully agreeing right up until Einstein's death in 1955. Most working physicists, meanwhile, put the question aside. Quantum mechanics worked. It made extraordinarily precise predictions that matched experiment after experiment, and it was being used successfully to build an entire modern technological world: transistors, lasers, nuclear physics. Whether there was some hidden deeper reality underneath it all seemed to a lot of people like a question you couldn't actually test, a question for philosophers rather than experimentalists. It was often described, somewhat dismissively, as an interpretational issue, not a scientific one, precisely because nobody could see how you design an experiment to distinguish between quantum mechanics as complete and quantum mechanics as incomplete, but the hidden variables happen to reproduce identical. Statistics, no matter what you do, And then in 1964, a physicist named John Stewart Bell did something nobody expected. He found a way to turn a philosophical argument into a testable prediction. This is the hinge point of the whole story. So let's slow down here, because Bell's insight is genuinely one of the most elegant pieces of reasoning in 20th century physics, and it deserves to be understood rather than just cited. Bell asked a very specific question. Suppose Einstein is right. Suppose there really are hidden variables, some definite properties that each entangled particle carries with it from the moment it's created, fully determining what result you'll get no matter which way you decide to measure it. And suppose, crucially, that these hidden variables are local, meaning that whatever information determines the outcome on one particle can't be instantaneously affected by a decision made far away on the other particle, because that would violate the speed limit imposed by relativity, the very thing Einstein was trying to protect in the first place. Given those two very reasonable sounding assumptions, locality and realism, Bell showed mathematically that there's a limit to how strongly correlated the measurement outcomes of two entangled particles can possibly be across a range of different measurement choices. This limit is now called Bell's inequality, and it's a real number, something you could actually calculate and, more importantly, actually measure in a lab. Let me try to give you a feel for how this works without drowning you in the algebra, because the structure of the argument is more important than the specific equation. Picture two detectors far apart, each one able to measure an incoming particle using one of a few different settings. Think of it like a dial that can be pointed in different directions. Each run of the experiment, you randomly pick a setting on each detector, fire off a pair of entangled particles, one to each side, and record whether each detector registers one outcome or another. Do this many thousands of times with the settings chosen randomly and independently at each side, and you build up statistics. How often do the two detectors agree, and how does that agreement rate change as you vary the combination of settings? If the particles are simply carrying predetermined local instructions, the hidden variables Einstein imagined, there's a hard mathematical ceiling on how correlated those detector readings can possibly get averaged across the different setting combinations. That ceiling is Bell's inequality. It doesn't matter how clever your hidden variable theory is, as long as it respects locality, meaning no faster than light influence between the two sides, you cannot beat that ceiling. It's not a matter of finding a smarter local theory. Bell proved it's mathematically impossible for any local realistic theory to do better. And here's the part that made this a turning point rather than just a clever proof. Quantum mechanics predicts that under the right conditions, the correlations between entangled particles will be stronger than Bell's inequality allows. Not infinitely stronger, not by an enormous margin, but measurably, unambiguously stronger, which meant that for the first time in 30 years, there was a real experiment you could run. You could create entangled particles, measure them in different combinations of settings, tabulate the statistics, and compare the number you got to the number Bell's inequality said was the absolute maximum allowed if local realism, Einstein's picture of the universe, were true. If your experimental number came in below the Bell limit, local realism survives. If it came in above the Bell limit, something in that picture, either locality or realism, or possibly both, has to go. This wasn't a small ask experimentally. Creating pairs of genuinely entangled particles, typically photons, and measuring their polarization or spin in different combinations with enough precision and enough repetitions to get statistically meaningful numbers was a serious technical challenge with the technology of the 1960s and 70s. But physicists took it on. The first real attempt came from John Clauser and Stuart Friedman in 1972 at Berkeley. They built an apparatus that generated pairs of entangled photons from a cascade of light emitted by calcium atoms and measured their polarization through a series of filters set at different angles. Running the numbers, they found a violation of Bell's inequality, a result consistent with quantum mechanics and inconsistent with local hidden variable theories. It was an enormously important result, but it wasn't airtight. There were what physicists call loopholes, gaps in the experimental design that a determined skeptic could point to and say, technically, this doesn't fully rule out local realism yet. because of some subtle assumption baked into the setup. The most famous of these loopholes is called the locality loophole. Here's the concern. If the two measurement stations, the two places where you're measuring each of the entangled particles, aren't far enough apart, or if the choice of which angle to measure at isn't made quickly enough and randomly enough, then in principle, some undetected slower than light signal could sneak between the two detectors during the experiment and coordinate the results, faking the appearance of quantum correlations through entirely mundane, local, physical means. It sounds almost paranoid, and in a sense it is, but that's exactly the kind of rigor you need when you're trying to rule out an entire category of physical theory, not just confirm a hunch. In 1982, Alain Aspect and his colleagues in France closed this loophole significantly further. Their setup allowed the choice of measurement angle at each detector to be switched extremely rapidly, faster than light could travel between the two measurement stations during the relevant window of time. If a hidden signal was going to coordinate the results, it would have had to travel faster than light to do it, which physics forbids. And once again, the results violated Bell's inequality, matching the predictions of quantum mechanics. Aspect's experiments became, for a whole generation of physicists, the textbook demonstration that something genuinely strange was going on, even though, as I mentioned, some loopholes remained. There was the detection loophole, the concern that if your detectors aren't efficient enough and you're only catching a fraction of the entangled pairs being produced, maybe the pairs you happen to detect are a biased, non-representative sample that could, through some conspiracy of imperfect equipment, fake a Bell violation even in a fundamentally local universe. Think of it like a bizarre kind of selection bias. If you only ever catch and interview the outcomes that happen to look correlated and quietly miss the ones that wouldn't have supported your conclusion, you can be fooled without anyone doing anything dishonest, simply because the sample isn't fair. There was also a deeper, more philosophical loophole called the freedom of choice loophole, the worry that if the random choice of measurement angle at each detector isn't actually random, if it's somehow correlated with the hidden variables from the moment the particles were created, perhaps by some common cause reaching back into the past, then the whole test could be undermined in a way no amount of clever engineering could fully close. This one is subtler and harder to shake because it questions whether experimenters ever truly have free, uncorrelated choices about what to measure, or whether the entire universe, in some deterministic sense, was already arranged from the beginning in a way that makes the randomness only apparent. Anton Zeilinger and his collaborators spent much of the following decades systematically attacking these remaining loopholes, one at a time, with increasingly sophisticated technology, better photon detectors, faster and more genuinely random switching mechanisms, longer separations between detection stations. And in 2015, several independent groups, including Zeilinger's team, along with groups led by Ronald Hansen in the Netherlands and others in the United States, finally ran what are called loophole-free Bell tests. These experiments closed the locality loophole and the detection loophole simultaneously in the same run, something that had never been achieved before. Some of these experiments even used an ingenious method called the cosmic Bell test, using the arrival of light from distant quasars, sources so far away that their light had been traveling toward Earth for billions of years, to help determine the random measurement settings, making it almost absurdly difficult to imagine any local, mundane mechanism that could have coordinated the results in advance, since doing so would require a conspiracy reaching back before the Earth itself existed. And the results across every one of these loophole-free tests violated Bell's inequality. Not once, not marginally, but consistently, decisively, in agreement with the predictions of quantum mechanics and in violation of what any local realistic theory could produce. In 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger for exactly this body of work. Experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The Nobel Committee citation was, in its own understated scientific language, an acknowledgement that this line of experiments had settled a question that had sat unresolved since 1935. Local realism, The picture of the universe Einstein wanted to be true is not how nature actually behaves. Now let's sit with what that actually means, because I don't want to just hand you the historical timeline and move on. I want you to understand why physicists describe this as an experiment that made them question reality itself, not just an interesting result about photons. Bell's theorem, remember, rested on two assumptions bundled together. Locality, meaning no instantaneous influence can travel between the two measurement points, and realism, meaning particles have definite properties independent of measurement. The properties are just hidden from us rather than genuinely undetermined. The experiments tell us that at least one of these assumptions has to be false. They don't, by themselves, tell you which one. And this is where physicists genuinely disagree, not about the experimental results, which are not in serious dispute, but about how to interpret what those results mean for the nature of reality. One option is to give up locality. This is the option that leads to language like spooky action at a distance, actually being, in some sense, real. Though it's crucial to understand this doesn't allow you to send an actual usable signal faster than light. The correlations show up only when you compare notes after the fact, by bringing the two sets of measurement results back together and comparing them through an ordinary, slower than light channel. So it doesn't violate relativity's speed limit on communication, even though it's deeply strange from the standpoint of our classical intuitions about cause and effect being confined to light cones. There's a specific alternative theory that takes this route explicitly called pilot wave theory, or de Broglie-Bohm theory, after the physicists who developed it. In this picture, particles do always have definite positions, satisfying Einstein's realism, but they're guided by an invisible wave that itself is non-local, instantaneously sensitive to the whole experimental setup, including the faraway detector. It reproduces every prediction of standard quantum mechanics, which is a remarkable achievement, but it does so by embracing the non-locality outright rather than trying to hide from it. The other option is to give up realism, to accept that particles genuinely do not possess definite properties prior to measurement, that the act of measurement isn't revealing a pre-existing fact, but is, in some sense, that's very hard to put into ordinary language, participating in bringing that fact into being. This is closer to the Copenhagen interpretation that Bohr was defending against Einstein all those decades ago, and the Bell test experiments are, in a real sense, a posthumous vindication of Bohr's side of that argument, though Bohr himself never lived to see the definitive experimental confirmation, having died in 1962, 2 years before Bell even published his theorem. There are other interpretations too, ones that try to preserve both locality and realism by giving up something else entirely, like the idea that there's only one single outcome to any measurement, which is the strategy behind the many worlds interpretation first proposed by Hugh Everett in 1957. In that picture, every possible measurement outcome actually happens, but in separate, non-communicating branches of reality, so that the version of you who measured one particle and the version of the universe containing the correlated result of the other particle are always consistent within their own branch, without any need for a signal to travel between them at all, because in a sense, all the branches were always there, unfolding together from a shared quantum state. It's a genuinely local theory in a strange sense, precisely because it refuses to single out one outcome as the outcome that has to be communicated anywhere. Then there are interpretations that reject the assumption of free choice in selecting measurement settings, sometimes called superdeterminism, which is a minority position but a logically consistent one, even if most physicists find it deeply unsatisfying because it seems to suggest that the entire universe was arranged from the Big Bang onward in a way that conspires to make experimenters choose measurement settings that produce exactly the correlations quantum mechanics predicts, which starts to feel less like physics and more like an elaborate cosmic coincidence with no explanatory power, a theory that technically can't be ruled out by any experiment, precisely because it denies the experimenters freedom to run a fair test in the first place, which is part of why most physicists set it aside, even though they can't strictly disprove it. What's genuinely remarkable, and what I think earns this story its place as the experiment that made physicists question reality, is that this isn't a debate about untestable philosophy anymore. the way it was in Einstein and Bohr's lifetime. The experimental fact that entangled particles display correlations too strong to be explained by any theory that is both local and realistic is now about as well established as any result in physics. What remains open, genuinely open, debated by serious physicists at serious institutions, is what that fact tells us about what reality fundamentally is. Does it mean influences really do propagate instantaneously across space in some sense that doesn't let you send a message but still represents a real physical connection? Does it mean the properties of particles genuinely don't exist until measured? That the universe is, at its most basic level, not a collection of objects with definite attributes, but something closer to a web of potential outcomes that only crystallize into definiteness through the act of interaction? These aren't rhetorical questions I'm going to neatly resolve for you at the end of this video, because they haven't been resolved, not by the people who've spent their entire careers on exactly this problem. It's worth mentioning, too, that this isn't only a philosophical curiosity anymore, sitting off to the side of real physics. The same entanglement that unsettled Einstein is now the working resource behind an entire emerging technological field. Quantum cryptography uses entanglement to create communication channels where any attempt at eavesdropping physically disturbs the correlations in a detectable way, offering a kind of security that doesn't rely on an eavesdropper simply not having enough computing power, the way most of today's encryption does, but on the actual laws of physics, making undetected eavesdropping impossible. Quantum computing, in its most ambitious forms, uses entangled states across many particles simultaneously to perform certain calculations in ways that would be effectively impossible for any classical computer to replicate in a reasonable amount of time. None of this would exist as an engineering discipline if the strange correlations Einstein dismissed as spooky hadn't turned out to be not just real, but reliably reproducible and eventually harnessable. I'll say this, though, because I think it's the most honest way to close the loop on Einstein's original discomfort. He wanted the universe to be the kind of place where things are real, definite, and locally caused, the kind of place his physical intuition, built from a lifetime of thinking about relativity and causality, told him it had to be. The experiments that eventually bore his name, the EPR experiments, ended up proving him wrong about that specific hope, decisively and repeatedly across nearly a century of increasingly rigorous tests. But I don't think that makes the story a defeat for him. I think it makes it one of the greatest examples in the history of science of someone asking exactly the right question, formulating it with such precision that it eventually became testable, even though the answer that came back wasn't the one he wanted. That's what a great scientist actually does. Not always being right, being precise enough in being wrong that the universe gets to correct you in a way everyone can verify. And that, I think, is the real reason this keeps physicists up at night, in a good way, the way a genuinely open, genuinely deep question should. We now know, with about as much certainty as physics ever grants us, that reality does not behave the way common sense insists it should, that objects are not simply carrying around a full set of hidden, predetermined properties waiting to be revealed, and that whatever is actually happening at the most fundamental level of the universe is stranger and more deeply interconnected than the picture any of us walk around with by default. The math has been confirmed, tested, and retested, closing every reasonable loophole skeptics could propose. The philosophy is still being written, and probably will be for a long time to come, because unlike most scientific disputes, this one isn't waiting on better instruments to settle it. It's waiting on us finding a better way to think about what the instruments have already unambiguously shown us. If you found this interesting, there's a lot more in this area worth exploring. From the details of how entanglement is actually generated and manipulated in modern quantum computing labs, to the ongoing debate between the different interpretations I mentioned today, Copenhagen, many worlds, pilot wave theory, and the handful of holdouts still defending some version of superdeterminism, to how these ideas connect to some of the deepest open questions in physics about the relationship between quantum mechanics and gravity, a puzzle that remains unsolved and that some physicists suspect may require yet another Bell theorem style breakthrough before it's finally cracked. Thanks for spending this hour thinking about something genuinely strange with me, and I'll see you in the next one.